Hello everyone, I am Sayantan and today I am going to present on energy efficient over-the-air computation assisted federated learning. This is a joint work with my research supervisor, Professor Nilesh B. Mehta. First, I will talk about federated learning and its applications. Next, we'll talk about a way to implement federated learning that is called over-the-air computation. Then we'll discuss our contribution, that is energy efficient and fast control descent algorithm, and then I will conclude. Federated learning is a distributed technique where a group of devices and a server collaboratively train a machine learning model. It enables smart devices to utilize their computational resources. Therefore, it decreases reliance on the server. Since every device has a local version of the machine learning model available all the time, it allows real-time data processing. And last but not the least, the devices only need to share their locally computed model through the wireless channel and not their local datasets. Therefore, federated learning inherently enhances data privacy. This technique has promising applications in the fields like autonomous vehicles, personalized AI assistants, large or cross-language models, and patient health forecasting. For example, an AI assistant named Siri can respond to its user because a speaker recognition model is collaboratively and continuously getting trained on the speaker's audio data across multiple devices. So let me set up the context. Consider a wireless network consisting of k devices. Device I has a dataset script di, and there is a central node called the parameter server. The goal is to find the optimal weight that minimizes the average loss across all data points across all devices. Under some technical conditions, an algorithm called the stochastic gradient descent converges to this optimal weight, which can be performed as follows. A device selects a mini batch of dataset uniformly at random from its local dataset and computes this term, which we call the local gradient. Then the devices send their local gradient to the parameter server, using which the parameter server updates the weight, and then it broadcasts the weight back to all the devices. And this algorithm goes on until convergence. The local gradients are high dimensional vectors. One way to transmit them to the parameter server is to send them over different time frequency resources. One salient feature about federated learning is that the parameter server only needs to know the sum of the local gradients and not the local gradients individually. This has motivated researchers to use over-the-air computation to implement federated learning. In this method, the local gradients are transmitted to the parameter server using amplitude modulation in a single time frequency resource. What happens in the baseband is that a device computes its local gradient, then it multiplies with the power coefficient and nullifies the phase of the channel. Then noise gets added at the receiver, and then the parameter server post processes this aggregated signal using a receiver amplification factor. Using the superposition principle of the signals, the parameter server gets an aggregated sum of the gradients, which changes the stochastic gradient descent algorithm step as follows. The step depends on the learning rate, the receiver amplification, the channel amplitude, and the transmit power coefficient. In this context, we address a couple of questions. First, how does this algorithm converge? For that, we prove a novel convergence analysis that characterizes the rate of contraction and the residual error in the global loss function in each iteration. It also identifies the trade-off between these two. The second question is how to adapt the transmit powers and the receiver amplification factor. For that, we find a novel power adaptation and receiver amplification rule that exploits this very trade-off between the contraction rate and the residual error. And the key takeaway of our work is that this algorithm is up to 80% more energy efficient than the conventional mean square error minimization scheme. We prove a recursive bound on the optimality gap, which is defined in an iteration as the difference between the global loss function value and the optimal global loss function value averaged over batch and noise. This recursive bound shows that the optimality gap in a certain iteration is upper bounded by a contraction factor alpha n multiplied by the optimality gap in the previous iteration, and there is some additive residual error. Now let us characterize this contraction and this residual error. The alpha n, we call it the rate of descent, that depends on these constants delta and L, which are specific to the global loss function. Additionally, it depends on this effective learning rate, which depends on the four parameters which I have talked about, that is the learning rate, the receiver amplification, the channel amplitude, and the transmit power coefficient. And the residual error, we term it as the error flow, which also depends on these four factors. Alongside with that, it also depends on the batch variance and the noise variance. Notice that if you increase transmit power of a single device, then the effective learning rate will increase, and in certain regime the rate of descent will decrease. That means we'll contract more in an iteration if we increase the transmit power. Also notice that increasing the transmit power increases the error flow. That means by increasing the transmit power, we contract more, but the residual error also increases. And this brings out the fundamental trade-off between the convergence rate of the algorithm and the error flow. Our goal is to adapt the device transmit powers and the receiver amplification such that the algorithm converges at a user-specified target learning rate, which we define as eta TGT, and we minimize the aggregate error flow over infinite time horizon. From the convergence analysis, we find out this upper bound on the aggregate error flow that we minimize subject to the constraint that at each iteration my effective learning rate is exactly equal to the target learning rate, and the second constraint is the peak power constraint that tells us when a device sends its local gradient, which is m-dimensional vector, it multiplies it with the power coefficient. Therefore, the average power spent over the whole local gradient should be less than the peak power limit of the amplifier of the device. The solution to this optimization problem can be computed numerically. However, in a certain regime, we can find out a closed form optimal solution. Before that, we need to know what is called a metric of a device. So device K sets its metric as the ratio between its channel amplitude and the L2 norm of the gradient it sends. And we have ordered the matrix of the devices, and theta square bracket K of n is the smallest of them. Having said that, now for a regime where this batch variance is much greater than the noise variance, the optimal solution is as follows. The transmit power depends on the dimension of the local gradient, the peak power, and it is inversely proportional to the square of the channel amplitude, and additionally it is proportional to the square of the smallest metric. The receiver amplification factor depends on the learning rate, the target learning rate, the dimension of the device, the peak power, and on the smallest metric. In other regimes, the advantages of using the solution is as follows. 1. The solution is causal. That means the transmit power allocation and receiver amplification in an iteration does not depend on the future values. Second, this is batch variance agnostic. The solution does not require the knowledge of the batch variance, which is difficult to compute and it changes with iteration. Third, this is a closed form solution, and if you know the smallest metric, other parameters are local to these devices. So the devices can compute them. Also the parameter server can compute them. All they want to know is the smallest metric. Fourth, the devices and a parameter server requires only the smallest metric. We benchmark the performance of our algorithm in a linear regression setup. We have synthetically generated the labels tau from a true weight, and x, the data, is a IID Gaussian random vector, and delta is the dataset noise, which is also Gaussian with unit variance. Each device has 500 data points, and there are such 20 devices in the network. Each device computes its local gradient using a mini batch of 100 data points selected uniformly at random from the 500 data points. The dimension of the weight and the local gradient is 10. The loss function is as follows, and to calculate the optimality gap, we need to know the value of W star, which is the optimal weight, and this can be calculated by stacking all the data vectors in a matrix called capital X and all the levels in the vector called tau. And the channel model we consider between the devices and the server is relay fading. Next, we see the evolution of the optimality gap as a function of iteration. For a system parameter of learning rate 0.1 by L, where L is the Lipschitz constant, and a peak signal to noise ratio, which is defined as the ratio between the peak power and the noise variance, we set it at 10 dB. In red is our scheme with a target learning rate of 1 by L. We see that for our scheme, the optimality gap decreases with iteration and then reaches an aggregate error floor. The error floor is around 10 power minus 2, which it reaches around 9 iterations. Next, we show in black is the conventional mean square error minimization scheme, that adapts to transmit power and the receiver amplification to minimize the mean square error between the aggregate and expected gradient, such that the devices satisfy the peak power constraint like ours. This solution has to be computed numerically. We see that for min-MSE also, it decreases with iteration and reaches an aggregate error floor which is lower than us, but it converges to that aggregate error floor around 500 iterations. So there is a 56x gain we get by employing EECDA with a target learning rate of 1 by L. Now for a fair comparison, we have slowed down the target learning rate of our algorithm and we show it in blue. The target learning rate of this blue curve is 0.1 by L, same as the min-MSE scheme. Still we see that it decreases to the aggregate error floor at an iteration of 100, and the difference between this aggregate error floor between the min-MSE and the EECDA decreases as the SNR increases, and for this case we get a 5x gain. Now remember that an iteration means all the devices need to transmit their local gradient to the server. Therefore it saves some energy, and we see that in the next slide. Next, we benchmark the energy consumption of these two schemes. We plot the sum energy consumed to achieve a given relative optimality gap. The sum energy is normalized by the symbol duration and the noise variance, and the relative optimality gap is also a normalization of the optimality gap by the optimal value of the global loss function. We have plotted for both the schemes. In red is the relative optimality gap of 10 power minus 2, and in blue is the relative optimality gap of 10 power minus 1 for the same set of parameters. Now we see that the sum energy increases as the SNR increases for both the schemes. However, EECDA's sum energy is markedly lower than the conventional scheme. For a SNR of 1 dB, EECDA takes 80% less energy than the conventional scheme, whereas this corresponding percentage decreases to 52% when this is high SNR regime. In conclusion, we have developed a novel recursive upper bound on the optimality gap, which brings out the trade-off between the rate of descent and the error floor. Based on this trade-off, we have developed an algorithm called EECDA that adapts the device transmit powers and the receiver amplification factor such that the algorithm converges at a target learning rate at each iteration, which is specified by the user, and it minimizes the aggregate error flow over infinite time horizon. And this adaptation is based on the smallest metric amongst all the devices. Thank you.